This video is about inverse tangent, inverse cotangent, inverse secant, and inverse cosecant. As always, begin by reading through the textbook and taking careful notes, but then also consider the following highlights. Just like we did when defining inverses for sine and cosine, which were previous topics, we will clip a portion of each function's graph to create one-to-one pieces of each graph so that it has an inverse that is a function. So to recall from algebra, a graph that passes the horizontal line test has an inverse that is a function. Well, trig functions, being periodic, do not pass the horizontal line test unless we clip and use only a portion of them, which we'll be doing here. And so, for the graph of tangent, where we'll begin, which, by the way, we introduced or developed in a previous topic. So if you want to review, the graph of tangent and some of those details of where they come from, that's fair. That was a previous topic. From here, we're just going to kind of take it from knowing what it looks like already, and we're going to use or clip a portion of it defined as follows. We're going to go from negative pi over 2 to positive pi over 2. Now you may recall that these trig functions are periodic and they keep repeating as you go to the left or to the right. And so the graph of tangent, which has characteristics we've seen, passing through the origin and then kind of snaking down to the left toward a vertical asymptote and then upward to the right toward a vertical asymptote. That pattern just keeps repeating as you would move to the left or to the right. You would keep seeing a repeat of that kind of stamped out repeatedly as you keep repeating those periods. So why focus on this one from negative pi over 2 to positive pi over 2? Well, it's just a convenient choice. It's not the only choice, but it's typically what's used in a math textbook, and so we're going to kind of follow that pattern. What that means is then we're going to define tangent, the graph of it being clipped. So y equals tangent of x, where x is between negative pi over 2 and positive pi over 2. So as shown in a graph, we know that there are vertical asymptotes at those two boundaries, right? At negative pi over 2, we have a vertical asymptote for the tangent function, and same thing at positive pi over 2. Of course, because the function is undefined there, as you can see if you go through the introductory video on the tangent function or graph. So what we're going to do is use this portion only. Now, when doing so, it might be helpful to visualize this portion on the unit circle. Some people find it easier to memorize visually, and that's totally fine. What I mean by that is if you just kind of draw or redraw or reimagine a unit circle, which we're familiar with by now, then you can see the portion of negative pi over 2 to positive pi over 2 would really mean the right half of this unit circle. Negative pi over 2 is at the bottom of the unit circle, positive pi over 2 is at the top of it. And so when we say we're using only this portion of tangent from negative pi over 2 to positive pi over 2, we're really talking about the right half of the unit circle. Again, visually that can help to remember what this little clipped boundary is. Now, in creating an inverse, which is an algebra topic, the same thing happens in trigonometry. Really, if you took every point on, for example, this graph of tangent that we've clipped, and I mean like any point whatsoever on the curve, each point has an x and y coordinate. If you were to reverse or switch those x and y coordinates and then plot those new reversed ones, you would get, well, the inverse function, which now we have pictured to the right. So you might see it denoted as tangent with a -1. That kind of looks like an exponent. It's not an exponent, it's just notation for inverse. Another name for it is arctan or arctangent. It's just another way to denote the same thing. It means tangent inverse. And if you then kind of imagine transforming the graph where you take every point and switch its x and y coordinates, it ends up being like a double reflection. And so the inverse graph for tangent resembles the graph of tangent that we've clipped, but it looks like it's, sideways. Well, it's actually a double reflection. So in other words, the inverse graph will pass through the origin. It will increase as you move to the right on the x-axis, but it will increase approaching what would now be a horizontal asymptote at positive pi over 2. And so it'll approach that just like the graph of tangent that we clipped, approached the asymptotes as you went left or right. Well, this one will approach it, but is now a horizontal asymptote. Or similarly, as you move to the left on the x-axis, the graph decreases for tangent inverse, but only as far as the horizontal asymptote at negative pi over 2. And so you get this snake-looking graph. It's a similar look as the tangent graph, but now it's kind of sideways, and increasing and decreasing as noted here. So it's important to recognize where this comes from and why. Remember, we're clipping only a portion of tangent, and when we do, notice that the inverse function, now that we've graphed it, it actually passes the horizontal line test, right? Any horizontal line would intersect this tangent inverse graph only once, which means, hey, this is a function by definition. Now let's move on to another, that's tangent. How about cotangent? Well, in a similar way, we're going to have to clip or chop a portion of the cotangent graph in order to make it one-to-one and therefore have an inverse that is a function. So just like we did with tangent above, we're going to do the same thing for cotangent, but it's clipped a bit differently, again, just for convenience. So you'll recall that the cotangent graph resembles tangent, but again, go back and review the introductory video lecture on cotangent graphs. And you'll recall that there's a vertical asymptote at 0 and also at pi. So they're kind of shifted over compared to the tangent graph. And then there would be, of course, an x-intercept in the center of that span, but then the cotangent graph increases to the left as it approaches that vertical asymptote, or decreases to the right in the same kind of way. And so for that reason, just for convenience, we're going to clip this function's graph by convention from 0 to pi. So we'll say y equals cotangent of x if x is from 0 to pi. And again, if you want to kind of visually recognize this from a unit circle, as many people find easier to remember or understand, then from 0 to pi, that would be really the top half of the unit circle, or you could say quadrants 1 and 2. Alright, so for that reason, we know where we'll clip the cotangent graph. If you create the inverse function of it in the same way we just did with tangent, which you could construct by switching every x and y coordinate of the points on the cotangent graph, you would end up with this inverse graph, which would intersect, or in other words, have a y-intercept at pi over 2. So that's corresponding with the x-intercept you would see in the portion we've cut. Now you're seeing the y-intercept. Remember, things are flipped or reflected twice, being an inverse. And as such, kind of like with the tangent function, now the horizontal asymptotes show up with the top one at pi, the bottom one at 0. And so you have the function for cotangent inverse approaching. As you go left on the x-axis, it approaches vertically that horizontal asymptote at pi, or as you move to the right, kind of decreases and approaches horizontally the horizontal asymptote at 0. And in similar notation, you could use a -1 for the cotangent inverse, or you could say arc cotangent, which is the same thing, and you'll see those used interchangeably depending on the textbook or what's being discussed. Again, notice that once we use this clip of the cotangent function, then you could create, or notice that vertical lines going through this cotangent inverse function intersected only once, which means it passes the vertical line test and it is a function. Now let's move on to some others in a similar kind of way. Note the following portions or domains used to create one-to-one graphs can vary per textbook or course. Okay, so if you, in other words, look back at what we just did with tangent and cotangent, you'll recall we cut them and used the portions, like for tangent it's -pi/2 to +pi/2, for cotangent it's 0 to pi, as noted and depicted Well, for the rest of these, for like secant and cosecant, the portions that are used actually can vary depending on the context, and so that just should be noted. This is not like the only way to clip these, but it's the way we're going to do it in keeping with our textbook and finding it convenient to use. It may not be obvious that it's convenient, however, when you take a look at them. So let's start with secant. We'll say y equals secant of x. And again, review the introduction to secant video if you want to look through the graph details on that again. But here's the deal. For this one, the portion we're going to use seems a little chopped up. But again, there's reason for it, as we'll see. But we're going to use the portion of 0 to pi over 2. And that would be reflected in part of that portion of the graph. If you take a look at the basic graph for secant, we're using only that little part of the graph, one of the branches that goes from 0 to pi over 2. It just looks like it looks like you're kind of chopping the branch in half to use that portion. That kind of is true, actually, but that's part of what we're going to use. Then we're going to move on and use a different portion as well, or another portion that's further to the right of it. This would be from pi to 3 pi over 2. So if you cut the branch where that is, it looks again like you're kind of chopping one of those branches in half. You'll recall the period for secant involves 2 branches. So a lot of this is built on the introduction we did to these graphs. It's good to review those if you feel like you need to get more comfortable with them. But the secant graph has these, kind of dueling branches within one period, surrounded by asymptotes, vertical asymptotes. And so we're going to chop and use only these 2 portions, which I'll admit seem a little random to be cutting it there, but there is convenience to doing so that we'll see going forward. So for now, we have to recognize where they're cut and just be okay using that. So once again, if you want to recognize it on a unit circle, which can be visually useful rather than just trying to rotely memorize these symbolic places we're chopping here. If you want to visualize where this is on the unit circle, then you'll note from 0 to pi over 2, that was the first piece we cut, that would be in quadrant 1. And then the second piece we cut, which was from pi to 3 pi over 2, that would be in quadrant 3. So these are kind of like opposing quadrants, and this is just where we're going to clip and use the secant function so that we're using a portion which passes the horizontal line test, which would mean, of course, that it has an inverse that is a function. So now, if we create the secant inverse function in the same way, that is, by reversing all the coordinates of every point that's within these little regions we're clipping from the secant function, if you switch all the x and y coordinates of all of those points, you end up with an inverse graph function that we can use for our purposes. So let's see if we can draw that. First of all, you'll have a point at the point -1 comma pi. And so we'll mark that on our graph. So the point -1 comma pi. We're just kind of marking this on here to draw the inverse. If I think of this as x and y, we're reversing all these coordinates from the original graph. So that would create, starting at the point -1 comma pi, a branch that would go upward, increasing to the left, but then approaching the horizontal asymptote at 3 pi over 2. You'll notice there's a vertical asymptote at 3 pi over 2 in the portion of the secant function that we've now clipped. So notice that's translating into a horizontal asymptote, which now our graph is approaching as it goes up in that direction. But that's not all. What about the other piece, right? Well, the other piece would start at the point 1 comma 0, and then it would increase, but then approach the horizontal asymptote that is at pi over 2. And so what you see are some interesting and slightly disorganized looking pieces, but let me color coordinate this to see if we can get this looking more familiar from what we were just seeing. If I coordinate the first branch I drew, or color it as orange, you can kind of see where that corresponds to the orange graph from the original secant function that we chopped. And likewise, I'll color coordinate the other one blue, the branch blue. And so you could also visually recognize that we're using really half. Remember, it's like you're cutting the branches from the secant function in half. So if you kind of visualize what the other halves would look like, you can kind of see, oh yeah, it's really just, double reflected to create this symmetry for an inverse graph. And we're just using these seemingly randomly clipped portions of the original graph, but it does actually help to use these portions, as we will see going forward. So we have y equals secant inverse of x, which of course, yes, you could call arcsecant as well. All right, let's carry on to our next one. This will now be the graph for cosecant. And again, we'll recall some of the things we've already seen for cosecant, and you can review that intro graph as needed. But you'll notice this time we have some things shifted around. There's some similarity between secant and cosecant, but different places for the vertical asymptotes and such. We still have, within one period, two branches, which we're going to have to just cut in half, kind of like we've been doing, just to create a function that's one-to-one, so that we can get an inverse that is also a function. For this one, we're going to look specifically between, so this is for cosecant of x, we're going to look from 0 to pi over 2. That will be our first portion. So I'm going to put this on here kind of all at the same time. So on our unit circle, again, to kind of recognize this visually, if we take 0 to pi over 2, really that's quadrant 1. And what you're finding is 1/2 of one of those branches is all we're grabbing from that portion there. And then the other piece we're going to use here is pi to 3 pi over 2. And again, on the unit circle, that would be really quadrant 3. And so that creates or borrows or uses the other portion of the graph here, but when clipped, we're grabbing portions that are one-to-one for our purposes of creating an inverse that is a function. Of course, we'll also find the corresponding asymptotes. So we have a vertical asymptote at pi in the cosecant function here. Now that's going to be a horizontal asymptote at pi. And so if we translate all these, or transform all these points that we would switch for x and y from the original function of cosecant to now its inverse function, cosecant inverse, we will find the following. There's a point at -1, 3 pi over 2, which we'll graph to start. So at -1, 3 pi over 2, I'm going to go ahead and plot a point. And then what we'd find is that this graph decreases as you move to the left, approaching the horizontal asymptote that is at pi. So it looks like half of the U-shaped branches of the original cosecant graph, and of course it's flipped around or double reflected. But that's one piece. The other piece would start at the point 1, pi over 2. So we'll mark that as well on here, 1, pi over 2, which is kind of halfway up the first half, the bottom half of what we're looking at. And then that branch would decrease and approach. There'd be a horizontal asymptote at 0. That branch would approach. So again, if we coordinate these by color to match things up, we have the first piece and the second piece corresponding to the places we're clipping or cutting to use a portion of the original cosecant graph that is one-to-one, so that when we create this inverse, and notice it works if you check it out now, the inverse we've created passes the vertical line test, just like we've been seeing. You can now cut any of that graph with a vertical line, and it will do so only one time. So as twisted as it can seem to get with these graphs, they're helpful to visualize and organize the information we know already from these trig functions, which kind of build all the way up from the unit circle. And now we're clipping them to, follow algebra's rules, creating a one-to-one function that has an inverse that is a function. And what we get are these results visually. But then practically, sometimes it's good to know how we could use them in more of an algebraic setting. Let's now try some examples where we want to find the exact value of each expression if it is defined. So this is less graphically oriented as we've been seeing, but more just kind of utilizing the definitions. We'll still recall the unit circle and things we need about properties of these functions here to make this possible. But for number 1, we have 3 expressions. So example 1a starts as the tangent inverse of -1. In other words, we want to evaluate what is that, if it is defined. Now, as a practical way of approaching this, what I'm going to suggest is that we turn that expression into a convenient variable. So I'm going to just pick on theta because it's a common trig variable. And I'm going to say theta equals our expression, tangent inverse of -1. Now, the reason I'm doing that is because what we can do then is take the tangent of both sides of this equation. We've seen these kinds of things done here before, so I'm going to take the tangent of both sides, which means I have tangent of theta on the left, and then I have tangent of the right side on the right, which was tangent inverse of -1. So what we're going to see now is a convenient cancellation property here. So you'll notice, and if you've read through the textbook, you will have noticed probably a little box in which they put these kinds of things. There's a cancellation property where you can say, if you look at the right side of our equation, we have the tangent of the tangent inverse. Well, those being inverses will cancel, which means we're left with the tangent of theta on the left side of our equation equal to -1 on the right side. So what we're looking for, of course, is theta, right? We kind of made up this theta variable. It wasn't in the original problem given to us, but we've tossed it in there representing that original expression that we're trying to evaluate. So in other words, if we can figure out what theta is, then we're done, right? So now we've gotten down to this place after taking the tangent of both sides and canceling the tangent and tangent inverse on the right side, where we know the tangent of theta equals -1. Well, really, if you think back, that's just kind of a unit circle question. So again, go back to your unit circle, which hopefully is pretty solidly memorized at this point. If not, keep writing it out. We want to know, where is the tangent equal to -1? You may recall that tangent, being sine over cosine, is +1 or -1 in the middle of various quadrants. So it turns out it's positive in quadrants 1 and 3 because the signs, SIGNs, of sine and cosine are the same there, but it's negative in quadrants 2 or 4. So where is tangent -1? Well, it's either quadrant 2 or quadrant 4. So the trick now is that we have to recall where tangent inverse is defined according to where it's cut in our definition above. So let's actually go back up to the farm where we started with tangent inverse way above. We were looking at its graph, so this was near the start of this topic's notes here. If you go all the way back up, you'll notice that was the first function we dealt with, tangent, and we said where we're going to clip or cut it to use a portion that would create an inverse, that is a function, and we said, as shown, that we're going to clip it from -π/2 to +π/2. We also said that to create an inverse, you simply switch the x and y coordinates of all the points, which essentially, as you may recall from algebra, switches the domain and the range. So for tangent inverse, let's just kind of put this together to make sure this is making sense. If you look at the tangent inverse graph, which we drew, it, of course, is stuck between vertically -π/2 and +π/2 because of where we clipped the tangent function to do that. But if we're looking at this inverse function, notice the domain of it goes on forever because it's just now kind of snaking through, which means the domain is really -infinity to +infinity, or all real numbers. However, the range, based on where we've clipped and restricted the original tangent function here, the range is stuck between -π/2 and +π/2. So we're going to mark that down because that's really helpful in us evaluating this expression. So just kind of note, we're adding this in back at what we already drew with the graph, but it's relevant because we want to know, in this case, if we're evaluating a tangent inverse graph or expression, it's got to have an output or a value that's within the range of -π/2 to +π/2. So now let's go way down to the problem we're working on now. we're trying to evaluate, here, we're trying to find the tangent inverse of -1. We've let theta be that. But if that's the case, then theta is really something in the range of tangent inverse. And that, of course, as we saw above, has to be in that -π/2 to +π/2 zone. So we're going to mark that down or kind of highlight. Our answer has to be somewhere in that span of really quadrant 1 or quadrant 4. What that does is boil it down for us, right? If the tangent of theta is -1, we know that the 1's are in the middle of each quadrant, but if it's negative, it's got to be in one of these we've now highlighted, which means it has to be in quadrant 4. Which means we could say then the theta that will get us there would be a -π/4. This really narrows it down for us because, again, we know that tangent of +π/4 would be a +1. We don't want that. We want it to be a negative. And we know it's not quadrant 2 because of the range of tangent inverse that we've restricted above. So it's got to be in quadrant 4, which means it's got to be -π/4. And yes, that is different than going in a positive direction to get to the same place. That would violate, this range we're working with, where theta has to be between -π/2 and +π/2. So that's how these things connect. If you go back up to those clips, those portions we've clipped above, you can see how they come into play when you're trying to evaluate even these basic expressions here. All right, let's try the next one. Part B says tangent inverse of π/3. All right, so we're going to approach this the same kind of way. I'm going to pull out a variable theta just to have something to work with and let that equal my expression. So theta equals tangent inverse of the square root of 3. Of course, it helps to use your unit, to know your unit circle on these. If I apply the tangent of both sides, or to both sides, I'll have tangent of theta on the left side equals tangent inverse of square root of 3 on the right side. And then if I use the cancellation property, tangent of tangent inverse, those will cancel, leaving us with the tangent of theta equal to the square root of 3. Now again, if you go back to your unit circle, you'll recall that the tangent value, which is sine over cosine, is square root of 3 or square root of 3 over 3 at many different places, even within one wrap of the circle. So to visualize it again, I'll just pull out a unit circle. And notice that this is positive square root of 3. Tangent is positive in quadrants 1 and 3. That kind of narrows it down for us. The question is which one? Well, in this case, again, we have to utilize the range of tangent inverse, since that's really what theta is representing. And as we just did, recall that tangent inverse is defined from -π/2 to +π/2. So really quadrants 1 or 4. And in this case, we're looking for where it is positive positive root 3, which would be in quadrant 1. That's where it's positive. And then the root 3 would be, if you can recall where the unit circle would hit, it's the upper place within that quadrant, which means theta there is π/3. Again, that's just kind of building from the unit circle and incorporating the restrictions we've now put in place from where we've had to clip tangent to create its inverse. Okay. So π/3 would be theta in this case, which represented this original expression in the problem. Okay, and thirdly, we have part C says tangent inverse of root 3 over 3. Well, this is very similar to what we just did, so let's kind of mark this down. If I let theta equal this, so I have theta equal to the tangent inverse of root 3 over 3. If I take the tangent of both sides, as we've been doing, I'm going to write this down here. Tangent of the left side means tangent of theta. Tangent of the right side, of course, tangent and tangent inverse would cancel. Okay, can we kind of skip writing that out by now? You'll notice that's happening in each case prior. The tangent of tangent inverse cancellation property, those are gone, which means we really have now the tangent of theta on the left equals, well, just square root of 3 over 3 on the right. That's all that would be left there after those cancel. So then, back to the unit circle, we're looking for where tangent is equal to positive root 3 over 3. Notice it's positive, which again would be quadrants 1 or 3 for where tangent is positive. Which of those is it? Well, we have to use the range of the tangent inverse, which hopefully now is becoming a little more familiar. It's quadrants 1 and 4, of course. Then the one that's within what we're looking at for a positive value tangent would be quadrant 1. Where is tangent equal to root 3 over 3? Well, again, you have your 3 places in your unit circle. Glance back at them. You'll recall root 3 over 3 is the first place there. And where does that happen? Well, that's when tangent is pi over 6, according to our unit circle. Okay, next our example says use a calculator to approximate the value of each expression to 5 decimal places. And the expression given is tangent inverse of 1.23456. Okay, well, let's take out a graphing calculator and find that you can easily type in this type of expression. So we'll go ahead and turn on our calculator, and notice that where the trig buttons are, as we've seen before, you have sine, cosine, and tangent. Above the tangent button says tangent with a little -1. That's your tangent inverse button. So we'll simply try by pressing secant and then the tangent button. Notice it puts tangent inverse in our graph, and we'll simply put the input of 1.23456 as given in there. Close parentheses, hit enter, and find an approximated decimal value here. It said to round to 5 decimal places, so we can do that. As seen there, this result would end up being approximately 0.88998, again, just given directly by the calculator. Okay, number 3, the next example says find the exact value of each expression if it is defined. And our first of those says tangent of the tangent inverse of 3 over 2. So we have kind of nested tangent and tangent inverse functions here. Now, you may wonder, well, can we just cancel the tangent and tangent inverse? I mean, we've kind of been seeing that cancellation property work for us already. The answer is, I think so, but let's double check to make sure everything's lining up. Sometimes with the cancellation and trig, we get into trouble with domains and ranges. So let's just verify, is the 3/2 that we're putting as the input for this tangent inverse function, is that a valid input? Well, input is domain. Let's go way back up to the ranch where we wrote out the domain and range of tangent inverse, just to make sure it's all fitting. Okay, way up here, we did this earlier. We saw the domain and range. We wrote it out for tangent. We didn't write it for all the others, but you could in the same kind of way. So it turns out the domain of tangent inverse is negative infinity to positive infinity, meaning all real numbers. So we have no problems with any inputs for tangent inverse, which is good to know. We're completely free to plug in whatever we want for tangent inverse, and the graph illustrates it as well. You have anything you can use with no vertical asymptotes in place here on the x-axis. And so, sure, because of that, and because we can plug in whatever we want to our tangent function, 3 over 2 is a valid input, which means we can simply use our cancellation properties. Tangent of tangent inverse, those cancel. The result is simply what's left, 3 over 2. Okay, our next example says find the sine of tangent inverse of -1. So notice we're kind of mixing now sine and tangent, which is fine to do because this is going to happen in a couple stages anyway. If you look back at what we were doing in the first set of expressions in our examples above, remember how we introduced this theta variable? And it was just kind of a convenient algebraic way to handle the problem. Well, let's do the same thing here, actually. So I'm going to look at what's inside my nested or composed functions. In the inner part, I have this tangent inverse of -1. We're going to let that inside part be theta. So let me write this over on the side where I have more space. I'm going to say this. Theta equals tangent inverse of -1. Now, why would I do that? Because now it's easy to see the algebra. I'm going to take the tangent of both sides of my equation. So I have tangent of theta on the left side equals tangent of the right side, which was tangent inverse of -1. So this actually resembles fairly closely what we were doing in our first example set above. And when I do this, of course, using the cancellation property, the tangent of tangent inverse, those cancel, which means we really have the tangent of theta on the left side equals, the only thing left on the right side is this -1. So again, back to the unit circle to figure out where we are. Where is tangent equal to -1? Again, it's 1 or -1 at all these center points of the quadrants of the unit circle. Of course, tangent is positive in quadrants 1 and 3. It's negative in quadrants 2 and 4. I'm just bringing back all this unit circle stuff. So we're looking at where it's negative, but of course, we're also looking at where the output of a tangent, in other words, the range of tangent inverse, actually is defined. As we've seen and noted above, that would be from -π/2 to +π/2, which really means we're talking only about quadrants 1 or 4 in this case. And so if we're looking for where it's -1, obviously that's got to be in quadrant 4. Where does that happen? Well, that's halfway down that quadrant, which means, in this case, theta must be -π/4. Negative means you're going clockwise rather, in through quadrant 4, halfway down. That's where that is. In that case, theta is -π/4. Now, in the examples we just did above, like in number 1, A, B, and C, we were pretty much done at this point because that's all we were looking for, right? Evaluating that expression. In this example now, number 3b, we're not done. That's part of what we're looking for. So now if I go back to this original expression, what I'm really working with is the sine of what I called theta, which was the tangent inverse of -1. We've just now figured out that theta is equal to -π/4. So really what I want is the sine of -π/4. I'm just now replacing. That's what we found theta to be. Well, this is now just a unit circle kind of question. And so you'll recall or go back and look at the unit circle. The sine of -π/4 would end up being a negative value, so it's going to be -√2/2. Again, just according to the unit circle values that we know. Let's try one more like this. Example C says the following. It starts as the sine of the tangent inverse of -√3. Well, it's going to build on pretty much exactly what we've been doing. I'm going to call the inner part, in this case, tangent inverse of -√3. We're going to give that a name that's just more convenient to use. And again, I'll use theta. Really, you could use any variable, but we've been using theta. So we'll stick with that, which means really I need to figure out what that is before I can find the sine of it, right? But as we saw, it's not too hard to put all this together. So let's, to use some space, conveniently move over to the right. I'm going to say theta, what I've just now named, equals that inner function, which is tangent inverse of -√3. All right, so I'm simply giving that a name. Yes, we're kind of making up that variable just to toss it in. It's just convenient. So now I'm going to take the tangent of both sides of the equation that we have going for us, which means on the left we have tangent of theta. On the right, we're going to have tangent of the tangent inverse of -√3. That was the right side, so now we're just taking the tangent of it. Of course, conveniently, then the tangent of the tangent inverse will cancel because of our cancellation property here. Those are inverse functions. We have a valid input for tangent inverse because, as we've already reviewed, it's all real numbers, so -√3 is no problem to plug in for that. And what that means is now we have the tangent of theta equals -√3, which takes us again back to the unit circle. So let's go ahead and redraw one of those and recall where this is. So tangent, of course, is positive in quadrants 1 and 3, negative in quadrants 2 and 4. and we're looking at negative root 3. So again, be familiar with where that is. And to restrict, remember, we're also looking at only quadrants 1 and 4 because of where tangent inverse is defined. And that's what we're trying to label theta, which was a tangent inverse expression. And so where is that defined? Well, according to what we said above, it's only quadrant 1 or quadrant 4. So let's see, where would negative root 3 be? Well, it's negative, so it's in quadrant 4. Root 3, if you'll recall the places on the unit circle, you have your 3 marks. Just root 3 itself would be at the lower mark of that quadrant, which means if we kind of label that appropriately, that would be negative pi over 3 for where that occurs. So that's again going clockwise into quadrant 4, to the third tick mark, so that's going a pi over 3 distance, but it's negative, so there it is. Remember, we're not done. That simply means that theta equals negative pi over 3. Great. Well, we care about the sine of theta. So we're looking for, in this case, the sine of what we've called theta. We just figured out that theta is negative pi over 3. So we're looking for really the sine of negative pi over 3, which again turns it into a unit circle problem. It's the same place we've been looking at already. So what is the sine value there? Well, it's in quadrant 4, so sine is negative. It would be negative root 3 over 2. Again, just going back to our unit circle values, confirming that to be the place where that is what sine of negative pi over 3 is. So put it all together and we've evaluated our expression.